When we look at showing that a function is continuous at a point, a lot of times, in fact, it's almost like a rite of passage for calculus students, is we really want to look at some piecewise functions where we can get some interesting behaviors and see if we can meet our definition of continuity at a point. So let's look at the function f of x, and we're going to be a piecewise function here. We're going to be the square root of x plus 3. And this is going to be true for values -3 less than or equal to x, less than or equal to 6. And we're going to be the piece x minus 3 for values x greater than 6. And so what we're going to be interested in here is we want to be able to show that f of x is continuous at x equals 6. And so we talked in the previous video about the 3 bullet points that we need to establish. We need to show that the function exists at 6, we need to show that the limit exists at 6, and then we need to state that those two things are equal if they are, and those 3 criteria will allow us to say that f of x is continuous at x equals 6. So let's start with our first bullet point. We need to say what f of 6 is. Well, if I look at the way my piecewise function is defined, I'm this top piece right here, the square root of x plus 3. For -3 less than or equal to x, less than or equal to 6. The equal to going into the 6 right there tells me that when I look at x equals 6, it gets substituted into this right here. So f of 6 is equal to the square root of 6 plus 3, which is the square root of 9, which is 3. So I've already said that f of 6 is equal to 3. There's one of the 3 things that I need to show. The next thing that I want to look at is I want to look for the limit as x approaches 6. And a lot of times with piecewise functions, especially if we're looking at where the function kind of breaks into a separate defined function here, I need to look at the one-sided limits. So let's take a look first at the limit as x approaches 6 from below of f of x. Here I'm talking about values that are slightly less than 6, but because they are less than 6, I'm going to look at this function right here. That's a well-behaved function. I can simply substitute 6 in, and I get the square root of 6 plus 3, which, as it was earlier, is equal to 3. The part that's going to be really interesting and really important is what happens when I look at the limit as x approaches 6 from above of f of x. Well, for values greater than 6 here, I need to look at this bottom piece, and I can do direct substitution there and say that's going to be 6 minus 3, and that equals 3. So here my one-sided limits match, so I can say the limit as x approaches 6 of f of x is equal to 3. So the limit exists, and that's the second bullet point that I had to reach, and I'm really almost there. In fact, it might be easy to rush in and say that we're done because you can see, hey, everything's coming out to be 3, and so therefore we're going to be able to say it's continuous. That's true, but we need to also make the claim that f of 6 is equal to 3, and that value here, so f of 6 was equal to 3, and 3 is equal to the limit as x approaches 6 of f of x. I know this seems maybe like it's trivial because it's sitting in there in your work. Everything came out to be 3, but you need to state this right here. This is kind of the big payoff, that third bullet point, that once we've made this statement, and this statement, then we can say, therefore f of x is continuous at x equals 6. And if we were to graph this piecewise function, it would be very easy to verify that there is no break in continuity at x equals 6, even though for this piecewise function at x equals 6 it gets redefined. It is continuous all throughout that point.